Welcome, my name is Omer Hamdi. I'm going to be your new TA.
Omer, you're here to stay?
Hopefully.
Yeah.
Yes, I'm here to stay. I'll upload my email to the Moodle system today. Feel free to send me messages. I'm also reside at room 513. In this floor, in the other side of the hallway, and I'm going to be your TA in Quantum Mechanics 1, which is cool. It's a nice course. It's very hard to understand and to get good intuition when you're trying to tackle the quantum mechanics for the first time. However, it should be quite technical and quite nice in the end of it. Okay, you are a small class, it's good, you can ask me many questions, so feel free. And I just briefly looked at your first 3 TAs, and I'm just gonna assume you know it, kind of. But feel free to stop me whenever, and I can elaborate. It's gonna be in your face. Perfect. So, we are interested in the Schrödinger equation. No. The Schrödinger equation, and I'm gonna leave it up here, is a wave equation where we have a derivative at time and a derivative in space, and we have some potential which depends on time and space. So, and this is what we're gonna solve. So if you're learning mathematical for physicists 3, what you're gonna do is you're gonna solve basically the Schrödinger equation 3 times. Here we're gonna repeat it in some manners, but also we're gonna do some stuff which are different. When we tackle this kind of equation, what we can do is, for example, try to guess a solution. We love to do it. Guessing a solution meaning we know what is the solution, or we have a good estimate of what the solution could be, and then we try and find some constant and try and see if it works. So for 1D, we can just guess the psi equals to some exponential of I omega t. Let's do kx minus omega t. Here the Laplacian becomes some second derivative in space. So what we guessed is basically a propagating wave, taking the derivative with respect to time, and I'm gonna use, sometimes I'm gonna say dou to the t or something, and sometimes I'm gonna do dou to the t like this. So feel comfortable with the 2 types of notation. So dou t psi will be minus I omega psi, and dou x squared psi is gonna be equal minus k squared psi, because we take I k twice, now I times 10 to minus 1. Hence the Schrödinger equation reduces to I h bar minus I omega psi equals minus h bar squared over 2, and we can have a plus, because of this one is k squared psi plus v r over t psi. Nice. So what we get here, we just eliminate the psi because it doesn't have any operations applying to it when we assume this potential. Hence we get that h bar omega equals h bar square of h bar square k square over 2m plus v. This relation is very nice because we know this is what we usually call the energy, and so h bar omega is the energy, and h bar k is the momentum. Meaning we got the relation that the energy equals to the momentum square over 2 plus the potential, which is quite nice because this is, yeah, it's very, very nice. It means that what we're doing in other courses also like coincide. We don't have any contradictions with the theory. Okay, this is 1-to-1. So a little bit
I have a question.
Yes.
The h bar k was P. That's in a momentum space or rotation space?
Maybe it sometimes can be confusing because sometimes you have P momentum equals mv, and then it's like in X space kind of, and sometimes you can have P operator, which is an operator in K space or even in real space. But I'm not gonna touch it right now. I'm gonna take it slowly. Perfect. I'm just gonna put here a few basic definitions. First, yes.
Tергול is Bermuda?
It will be.
Okay.
After the Tרגול. So, some basic definitions I'm gonna write down just to make sure you are comfortable with. Is that okay? So psi is the wave function, but we don't actually measure psi. What we measure is psi bigger psi, which is a probability. And because it's a probability, we denote it as rho. We say the probability to be at some place x at some time t is psi bigger psi, or psi absolute value squared. The probability to be in some place, if we're talking, this is about one digit, it can be easily generalized with some x vector. If you want to see what is the probability to be in some intermediate A to B, the probability that the particle is at some place between A and B, we can say it's an integral from A to B dx, rho of x comma t.
If we talk about continuous vector spaces, how can the probability not be zero for one point? Like if I plug in psi squared.
Yeah, this is okay. I'm gonna make it more accurate. This is the probability density. The probability to be, the probability of being between x and x plus delta x, or we can even say x plus dx is going to be rho of x comma t dx, which is what we have here. You're right.
So if they ask me, for example, to know what is the probability to be at time say t at x 5, I just plug in 5, or I just say no, it can't be because it's 1 point.
You plug in 5 and say the probability density to be.
Okay.
If you want to be very accurate, because it is a density, right? The probability to be at some specific place at some specific time is basically 0 or infinitesimal. However, if you multiply it by the x, it has some meaning. Okay. Especially when you have here delta x and you have here delta x, which is not very accurate because it's going to be true only when delta x goes to 0. But when you put it under an integral or summation, if you have a discrete system, it gets some meaning. Okay, perfect. Keep asking questions. It's very good. Okay, So this is for 1D. We got the energy relation. It's very, very easy. I'm gonna delete it now, and I'm gonna do it a little bit more serious. Okay, what we're gonna do is we're gonna solve the Schrödinger equation when, for one dimension, when the potential is independent of time. Then we have some general potential V. However, V of R, comma T is equal to V of R, meaning we don't have any dependence of time. Or we can say X if you want to be in one dimension. And what we want to do is we want to solve the Schrödinger equation. How are we going to do it? Because V is independent of T, it's very easy to just do a separation of variables. We're going to say that psi of X, comma T is going to be equal to some phi of X times some capital T of T. Then we're going to plug it in and see if it works, what we're going to get, and try to play with the system. So if I plug it in, I get I h bar dot T of psi is going to give me phi of X times capital T of T dot equals, then Laplacian becomes a spatial derivative, and so we're going to get minus h bar square over 2m T of T times phi common double derivative here. Perfect. Plus V times T of T times V of X. What we do in these situations, when you have some complicated object, we just divide by T of T and phi of X to see the separation of variables more clearly. Also, from this time forward, I'm just going to write capital T and phi. So I h bar T dot over T equals minus h bar square over 2m V double prime V plus V. Okay, so what we get here, we get two functions. We can call this some f of t, and you can call it, this part is going to be called f of t, this part is going to be called g of t. The g of x. Thank you. And when we have some function of t equals to some function of x, the only way we're going to have a solution for every t and x is when these two parts equal some constant. What should we call this constant? Energy. Perfect. Very good. Because energy is a constant. Okay. Very, very nice. So now we just need to solve two ordinary differential equations, one in time, one in space. Both of them equals a constant.
This is still one dimension?
This is, yeah, one dimension.
Okay.
Where do you see the one dimensionality? When we change the Laplace to some second derivative. We could have here higher order dimensions, but we start slow. Okay. For the time, for the part of the time, the 20 time, we have I h bar T dot equals E T. Do you have an idea what the solution for this part is? What's the solution? Yeah, exponential, perfect. So we can say that the guess, say T of T equals some T0, the I. I'm also making sure I don't have any omega 5 so far. And then even what is T0. Very good, we'll see. And what we get, we're going to get, so I multiplied by I is minus 1, so minus h bar omega t equals e minus I. Okay, minus. The reason I put a minus is the difference has to. Maybe we should go with glass.
Yeah. אני כאילו לא כזה, אז אני משתדל להפנות הרס למיטליה. הוא צונן. מה? לקבל את זה בהכנעה. כן, זה פשוט לא יודע למה, אני דווקא אחד שלא מרבה, כאילו אני אוהב.
להיות חולה.
בלי קשר, אני לא מרבה ללכת מכות סיני לפי הקשקל, אני אוהב דווקא להיות בגדלים מרבים. זהו, משום הצטרן. אז כנראה זה משהו ויראלי שאיכשהו הגיע אליי כאילו.
גם חום וזה?
חום לא, אבל כאב לי הגרון ועכשיו פשוט נזלת. הנזלת גם מוזרה כזו, אבל... האמת זה...
אולי אתה צריך מסכה.
זהו, היה לי כל פעם באוניברסיטה, המרצה היה מצונן, אז הוא אמר, אני בא עם מסכה כדי לא להדליק אותי.
יואו, אז אולי תהיה כמוהו.
Okay, we will continue here because we need
זהו,
to.
רעיון טוב, אבל יש אין לי מסכות.
And so we're gonna continue, okay? It's got very quiet. Thank God. So from here we get the relation E equals h bar
We
omega.
talked about the minus.
You talked about the minus. Why could I define the minus? Let's say I didn't define the minus. Let's say I put here minus and here minus, right? It's not gonna diverge because it's imaginary.
What's the
Diverge זה להתבדל.
Ah.
It's not gonna להתבדל or diverge because we have here an I, an imaginary part. Meaning I can write it as cosine plus sine. Plus I sine, it's oscillating function. Let's say we didn't put here the minus. It's gonna impact the omega. Because I'm gonna get basically omega I invented this variable. I can write omega equals minus E over H bar. Meaning T of T equals T0 E at minus I E over H bar T.
So you mean you just put the minus into the omega?
Yes, if I'm gonna put, let's put all the
So this
minuses.
is really not
No, both of them, if I put here minus, I'm gonna put here plus, and here plus, and here plus. I'm gonna have minus I, minus from here, but here I'm gonna have a plus. I'm gonna get the same solution. Why put the minus? Just for convenience.
No, if you divide
It
by
didn't
I,
matter. It didn't matter if I'm gonna put here minus or not.
but still we get it if you divide by I, because one over I is 1. Right?
Yeah, I put here the minus. And,
I understand.
because capital T is still the same function. So what we got here? First, we did even if it was a plus, it wouldn't diverge or itbadel.
because of I.
Because if I take T to infinity or T to minus infinity or to 0, I still will get something finite. Imagine. Also, we didn't find T0. We did get an expression in terms of E, which is good. I wanted to do it because I want to get some special expression in terms of E. But T0 we will be able to gain only from the initial conditions or boundary conditions. Okay? Which we don't have at time. Right now. Perfect. Any questions? That's okay. Okay, the special part is gonna be quite easy because we did the partial and the time part. So what we have here is, and we can write it as some minus h bar square over 2m psi, second derivative over psi, equals e minus v. We will later in this course discuss what happens when v is larger than e or smaller than e. It's very interesting. But we're going to assume e is larger than v for the moment. Why? Because otherwise we're going to get something different. So, psi, second derivative over psi, or we can say, yes, let's do psi second derivative over psi, is equal to minus h bar squared over 2m e minus v. Let's make it a little bit prettier. Okay. What are the solutions for this equation? We can do exponentials, sum of two exponentials. We can also do... Yes, of course. Perfect. Of course we need to. Okay. So, what we got here? Let's see. What are the solutions? What would you assume the solution can be? I'm going to wait here for an hour even.
Cosine and sine and exponential.
Perfect. We can have either cosine and sine or a sum of exponentials. So what we're going to do is, let's see how I want to do it. Okay. They didn't. Oh. So, what we're going to do, we can say that phi of x is some a sine of x plus b cosine of x. We can also say it is equals to a sine of x plus phi. Let's do here different a tilde. We can also say it's a hat e at kx plus b e b minus kx. Here it's kx. We can choose different coefficients described in different ways. However, I'm not gonna solve it explicitly right now because I want to move on. Basically, we just need to put it inside here, take the second derivative, and find some condition on k. Okay?
What did you say? Sorry.
What we're going to do from here on, the recipe is to plug phi of x inside this equation. Phi of x and then the second derivative of phi of x, and find some condition on k. In the similar manner as we found some condition on omega.
Wait, shouldn't there be an I there? Oh yeah.
Right. We can have k. Let's say this is k tilde and k maybe complex. It doesn't matter.
Okay.
Because also here I didn't have to vote I. If I didn't vote I, what I would get still that omega equals, let's say I didn't vote the I, what I would get is E and I. Okay? Because I'm gonna have, because you could do the algebra. Perfect. So, what have we got? Let's say this is, we're going to get phi of x in terms of k, and we're going to get k in terms of of some we're going to get some condition over E. But the bottom line is, and what I'm going to work with, because I don't want to go ahead on myself, is we're going to get some psi of x, comma t. We're going to get a solution which looks like t of t, which is going to be like t0 e at minus I t over h by t, and some phi of x. However, this is only one solution, because we will see soon that we're going to have a full space of solutions, because we're going to get some condition on k, which is going to be quantized, the options of available k. And maybe if we have time at the end of the class, we're going to do it. Just want to go through everything. So, so what we're going to get here, we're going to repeat it. We're going to get the quantization over phi n of x, which is going to be dependent of some kn. And then we can do it really quick. Okay, let's do it really quick. You want to do it? No? Okay. We leave it also for homework, and also we'll do it again in future classes.
I have that in the...
You have it in also in... yes. No, you don't have it here. But it's fine. I'm gonna upload it to you.
Okay.
I'm supposed to do it. Doesn't matter. But we're gonna get phi n of x theorem. So basically what we're gonna get some constant a or b, let's even call it c of n. And we're gonna get that we need to, because it's gonna be for some specific n, we're gonna get a series over on n from 0 to infinity. Because we need to, if we have one solution which depends on some quantization or some law of n, we need to consider all the possible solutions. Yes.
If we say that k could be complex, shouldn't we sum from n equals minus infinity? Because complex, complicated stuff, they aren't linearly dependent.
Okay, let's do it.
Yes.
I think it will be the best. I'm sorry. Let's do it. Okay. A son of kx plus b of cosine kx. Phi comma of x is gonna be a k sine of kx minus b k cosine of kx. Correct me if I'm wrong. It's gonna be cosine. You didn't correct me. It's gonna be minus a k squared sine of kx. Cosine, again, this is sine. And this is gonna be minus b k squared cosine of kx. Okay. If we're gonna assume some hard boundary conditions, meaning that we have some okay. We're gonna get back to this point. We're gonna consider the example of infinite potential hole. So, which means I'm gonna leave this t of t and we're gonna solve it for some specific example. It will be a lot easier. For the infinite potential well case, what we're gonna have, okay, so I have t of t, phi of x, and I'm gonna write here that psi of x comma t is equal t of t times phi of x. And we're gonna solve this in 1 minute. Okay. Let's assume a specific potential to make this solvable. We're gonna assume v of x equals 0 for x between a to 0 and infinity otherwise. Meaning from 0 to a we have no potential. This is v of x as a function of x. However, in this zone and in this zone, we're gonna have infinitely large potential. What it means is that the weight function phi of x given t will be 0 for x which is larger than a, or x smaller than 0. For any time and for any x which is not in this regime, we're going to get just 0 for the wave function. Okay, because the potential is infinite, so it's impossible for the particle to get there. Okay. How does it help us solve this problem? It helps us to solve this problem because I know that phi of x must also apply those same boundary conditions. So phi of x which is larger or equal to a, or x which is smaller than or equal to 0, must be equal to.
Also, the continuity doesn't need to be in the potential but in the wave function, because in electromagnetism we said that the potential must always be continuous.
Yes.
So now
But you also did a full example of where the potential is not continuous. Because, for example, when you have a spherical object which has some specific potential on it, so you assume it's not continuous. But in nature it's like it's supposed to be continuous in nature. The wave function must be continuous. What we have here is in a sense a toy model, meaning it's not something, you don't really have an infinite potential wall. You always have a finite potential wall, and when you have a finite potential wall you get different effects.
Oh.
So like you can't have infinitely, you can have approximately infinite.
Okay.
Okay?
Yes, yes.
So when we assume this, we can say that because we don't care about this area, this area and this area, only about the happy area, we want to check what is phi of x equals 0. It's going to be 0. And phi of x equals a is also going to be 0. This is what I needed to keep on with this solution. I had to have boundary conditions. Like here I had boundary conditions for time, where I said thank you. Perfect. So, when I have these boundary conditions, I can put it inside here to get that phi of x equals 0 equals a times 0 plus b. Cosine of 0 is 0, cosine of 0 is 1. This must be equals to 0, meaning b is 0. And when we have those kind of differential equations, usually when we have two boundary conditions where you must get a 0 and you have some sinus and cosine, the cosine disappears because it can't satisfy these boundary conditions. So you can just remove this part, and this part. Make sense what I did
Is
here?
it cosine, right?
Yes, because b equals 0.
Ah.
You could just put b 0, b 0.
Okay.
Okay. And also, what I also need to do is I need to put the other boundary condition. Phi of x equals a is 0, meaning So, because phi of x given a is equal to 0, a sine of ka must be equal to 0. Hence, we get a condition on k that ka must be equal to some n, where n is some integer, times pi. Got it?
Yeah.
Perfect. So case. So k becomes k of n.
Immediately B.
Said the b equals 0 because of the boundary condition.
Get that.
You mean for the second condition?
Yeah.
But for the first condition, b must be 0 because we can have a contribution for the cosine.
Okay.
Because if you're going to have here cosine leading, it's going to look something like starting from 1 or some constant. And we don't allow, we must have here 0 in this boundary.
But in a symmetric system, we would need to have both options, right?
Symmetric?
Like a over 2 to minus a over 2.
No, we're still going to have only sinus because if it's not about the symmetry of the system, because this system is symmetric. We can just change the coordinates to be at a over 2, be the 0 point. However, the cosine disappears not because of the symmetry, it disappears because of the boundary condition. When you have a boundary condition, I think it's called the the Richle boundary condition always confused between two, meaning it must be 0. The wave function, the two edges or the two boundaries, you only have sinus. On the other hand, if you had one side, for example here, it would be some constant, and the other side would be 0. You might, depending on the question itself, you might have only cosine of x.
Oh, we can ask you something after the table?
Yes, of course. Anyways, recap. We were trying to find the wave function, psi of x of t. We found the time part, and now we find the spatial part. Almost. Why almost? Because we still need to plot what I got for phi of x inside this equation. Okay? So, what I'm gonna do, I'm gonna write here in the left half and the right half. I'm gonna say what we have so far. We have phi of x equals a sine of kn x, where kn equals to n pi over a. I'm trying to use my time between the between the noise. So, and like I said, psi second derivative of phi multiplied is equal to minus kn squared a sine of kn x. Right? Correct me if I'm wrong. Check me. K squared n times phi of x. We are happy. Perfect. If I plot it here, phi of x divided by minus k squared of n times phi of x, or the other way around, is equals to minus k squared n.
Times a, right?
Why a?
Because you want to know the amplitude.
I know that phi, the second derivative of phi of x, equals to minus k squared of n times phi of x.
Yeah.
I can divide phi of x on both sides and get this. So here the minus is important, as I said. So I can just remove it. Let's put here a plus. Okay, and why it's important? Because what I'm going to get here, I'm going to get kn is equals 1 over Let's do 1 over h bar square root of 2m e minus v. Remember when I said e is larger than v? Because if e is smaller than v, we got a complex number. We get something which is acting very, very weird, and we're going to get back to it. About what we're going to see. We're going to get back to this part, what happens when e is smaller than v. But we assume here e is larger than v. But you say, hey, but we have v is infinite. No, where v is infinitely large, we don't have any wave function. We consider only the part when v is equal to 0.
If
yes.
A is complex, we get same, right? Maybe something. We get like hyperbolic.
Not gonna answer it right now.
Okay.
I'm not sure even. Maybe we'll get back to it. Okay, so we can say that for x between a and 0, kn equals square root of 2me divided by h bar. This is very similar to saying p is equal p squared over 2m is equal e, in some sense. Because multiply here, okay? Because what actually we get that E, the energy is quantized. Then we get h bar kn squared equals 2m e, and because this n gets a lot of possibility, kn can be a lot of numbers. It could be pi over a, 2 pi over n, and so on. H bar is constant, 2 is constant, and m is constant, and the only free parameter is e. Then we get en. Oh wow! Wow! This is amazing!
Is it like the... Wait, can I ask you something?
Yes?
If we say that K is like from the boy identity or something, K is like potential, then we get...
K is not potential. K is...
No, act, but if we get...
It's similar to momentum.
Momentum, right, sorry, momentum. Then we get...
we get what we got in the start, the beginning, where the energy equation of where the energy is equals to momentum with the potential, but here we don't have a potential. Let's write the full answer.
But if we get different quantized levels of energy, it's like I forgot the Bohr's.
It's very related to when you have a parabolic potential, which looks like this, and you get the energy levels. You get this quantization, right? So when you have sometimes what you see is something that looks like this.
Yeah, okay.
And then you say, okay, here it's parabolic, close the parabolic, and you have some discretizations of the energy. So this is very similar. We have here something, let's say here it's parabolic, here like, and here it's like square.
You say the atom is like infinite as well?
I'm saying the boundary conditions describe the quantization of the problem. Because when we don't have any boundary conditions, for example, when we have a free propagated wave, what we have is we have an infinitely number of energy levels. We don't have the quantization in the energy levels. When the particle is free, we don't have any quantizations in the energy. We can have any kind of energy.
Because it can escape to infinity. Okay.
Yes. Questions? Okay, let's write the full expression. Yes, we have time. It's good we have time. We're doing great. Psi of x comma t is equal. Now it's easier to understand what I did so far. Is equal, and I can write here t0 e to minus I e n. I'm going to write en. I can also write it in terms of h bar squared k squared over 2n. But let's write the n, because this is what we used to see. H bar t times that we're going to get. And because we have a quantization over n, we're going to get quantization over also the coefficients. Okay, we're going to see it very soon. What? And we get some an sine of, and instead of kn, I can just write n pi over a. So n pi x over a. I'm gonna do one simple thing. I'm gonna take this an and t0, t naught, to be some constant, because t naught is a constant. So I can just write here cn, some general constant. I'm allowed to. And because I have a function which depends on n, this is 5xt of n for some for a single mode. However, I can say what is okay. Let's do this 5x of t of n, but psi of x given t is going to be a sum over n equals 0 to infinity psi n of x comma t. Okay, this is a little bit different, but it's almost the same. The difference is the mode. Here it's for a single mode, a single n, and here is the full wave function. So what I'm going to do, I'm going to write here n equals 0 to infinity, and I'm going to move this n to save some space. Okay, this is very important expression. What we have here, we have a wave. We have a wave which can be any function in the intermediate 0a. We know it because we learned about Sturm-Liouville, or we will learn about Sturm-Liouville in our other courses, where this sine of x can, how do you say, lifros?
Span.
Can span all the space, exactly, with this coefficient cn's. And we have something which is oscillating in time. Okay? So each point is going to be described by some cn sinus of n pi x over a at a specific time point, and then it's going to oscillate according to this part. Meaning, the particles will always move at time. Even if they are somehow local exponents, which they are not. We will learn about it later, that they can be at some place. They always move both in time and space. Always. You're going to have something which is moving all the time. Okay. Now, this is important. This is very, very nice. We go to a very nice point. Yes.
Alongside the wave, and the wave is moving as well.
The wave, this is a wave of what?
The probability.
It's a wave of probability. That's a wave. It's a wave of probability. It's hard to grasp that. The idea is it's not a specific particle. When we look at quantum particles, we usually look at it as waves, and usually look at it as particles. So when you think of a wave, you say, okay, it's not a particle. The particle is, instead of being circle, it's a wave. It's not exactly true. It's somewhat true, but it's a wave of probability. Meaning, if the wave of probability looks like this, the particle is probably here. Probably.
Okay.
But if it looks that it could be, let's say, uniformly distributed, then the particle could be anywhere with the same probability. Anywhere inside the potential.
The fact that it moves is because it evolves with time. Otherwise, it would be some expected value of x.
Yes, if for a specific time, you can say, okay, the probability changes over different times. Okay, very, very nice. Okay. So, usually, let's look at this sine of x. How does it look like? How does the first few modes look like? So, if you consider the first few modes, we're going to get, for example, for sine pi x over a, we're going to get this. So this is the first mode. First mode meaning the first n, meaning n equals 1, because here n equals 0, what we're going to get? We're going to get 0. So I can place it as 1. But because n equals 0, here sine of 0, it's 0. So the first mode is n equals 0. N equals 1, right? We're going to get this shape because of the sine. The time part is going to oscillate it to become something like this. So we get here and back. So it's like going down and back up. Okay, because it's like multiplying by some constant. Perfect. The second mode, for example, yes, 1 second. And this is, yes.
If you say that the time makes it move to the negative roots, but still, how does it change anything? Because if you use the probability to square it and you put absolute value in square it, then it doesn't change.
Right.
So it doesn't evolve in time?
It gets a phase over time.
So what is the meaning of it?
So we'll get to examples soon.
Okay.
And then we will talk about it. So this is the n equals 1, this is n equals 2, and so on and so on. We can have, for example, n equal 3 is going to be something like this. This is n equal 3. Okay, perfect. And so on. But when we have all the possible n's, we can describe all the possible functions in this intermediate. Okay, nice. So, what I did here, I did a little bit I'm gonna give you some pieces to output the node. Perfect. Okay, so I did a little bit of stretching of it too, because this is true. However, what we would like to do, we would like to add here another constant. We can call it an, or previously known an, and I want to shoot it in a way such that this is normalized. We'll talk about it in a few moments. What does it mean? Meaning, we can have here some concept mathematically. What I had here without the a is true mathematically, also physically in some sense. However, it's easy. It's good measure to have here something which is normalized for the special. Okay, perfect. How are we going to find this normalization? What does it mean?
The integral of the entire interval. The probability density should be 1.
Yes. Yes, it is true. But what I want to say is that the probability density of phi of x, which is phi dagger of x, phi of x, this is rho of x.
You do like a projection maybe? You do a projection because these are the eigenvectors and you can do that.
1 second. So we want that the integral of rho of x dx will also be equal 1. Perfect. How do we do it? I'm going to do it here in this box and then move to the right side. And I can move this part because we finish with it. So what I'm going to do, I'm just going to say, okay, this is X. When I have here phi dagger, phi, it's a little bit confused. What do I mean? What I actually mean, because this is quantized in this way, I want to say that when I do an integral over, and this is phi n of x, and this is, and I don't need the dagger because it's all real. Phi n of x, dx, I would make it, I want it to be equal to delta and n, conical delta. Okay, because when we have two different modes, from orthogonality it's going to be equals, but when we have the same one, we want it to be equal 1. So I can write it. So I can leave it for an exercise to home to show that an integral over sine of n pi x over a sine n pi x over a dx from 0 to a. Why from 0 to a? Because this is all boundaries. If it was from minus infinity to infinity, fine, but here it's from 0 to a. This is equal to 0 always when n is different than n. We do this exercise a lot.
When you write the m, you mean that there is another, it's the same, sorry.
Yeah, you can do it in Hebrew.
כאילו m זה n ספציפי?
M is some specific mode. It's the same as n. I can write, you agree with me? N is a dummy variable, meaning I can choose to call it whatever. I can call it L, 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 L.
כאילו הכוונה הוא מגיע מתוך הסכימה על n, זה לא כאילו סכימה נוספת. כאילו אני סוכמת על n, 1, 2, מתי שמגיע ל-m, מתי שמגיע ל-m.
לא.
לא, אז מה?
לא. זה n כללי ו-n כללי. And it's a general n and general n, meaning n could be, for example, 5, and m could be 2, or m could be 6, or m could be also 5. Okay. It's some general variable. It's like a variable, it's a משתנה. כללי. What we want to show here is normalization in the sense that we know for different integer values of n and n, this will give us 0. We can just put it in Mathematica also, or in some rule from alpha, it will give us 0. We can also derive it ourselves if we have enough courage. However, for the same values, n equals m, we will make it equal 1. Because what I have here is a little bit, I forgot here a and a m. For the n and the m. But it doesn't matter because it equals 0. Okay, so for m, which is equal n, what we're going to get? We're going to get an integral over phi n of x, phi n of x dx, and we're going to say it must be equal to 1. This is equal to an squared times sine squared of n pi x over a dx from 0 to a.
The value of the integral
The value of the integral is
n squared times a over 2.
Yes. Well, how I like to write it is I like to write it as 1 over an squared equals the interval. But you're right. It's now for how we prefer. And here this is equals to a over 2, as you said. So an squared is equal to 2 over a. Now one could be very tempted to say an is equal to square root of 2 over a. However, this is almost true, because I can also have here some phase. E and I, let's say, let's do I, theta, here. Why can I do it? Because this is what we have here, is because here we have a dagger, we assume an is some real. But because here we have a dagger, what we have here is an absolute value squared. So here we have an absolute value squared, and here we have an absolute value squared. And when I take the absolute value square of this time, I'm going to get, when I take, let's do it like this, 2i. I'm going to get 2 over a, yeah, I, theta, times 2 over a, 8 minus I theta, which is 2 over a. So the math allows us to have some exponential of I theta. Why is it? What is it? This is something we call a phase. This is some phase. So when you measure it, like you said before, in the constant an, I'm not going to measure it. I'm not going to see it. This is going to be here, like when I take the absolute value. So I'm not going to see it. So why do I care? In this specific problem, I don't care, because I have only one general phase in this specific problem. However, meaning I can rewrite this an as square root of 2 over a ei theta. You agree with what I did? Mm. You agree? Yeah? So, because in this expression the only phase is here, I can always choose, and also you learn it in electromagnetic waves and in the wave school, so I can always choose one global phase to be whatever I want. I can always do it. Why? Because when I have a system and I measure with respect to some phase which I don't know. So when I start measuring, if I have two objects which have theta 1 phase and theta 2 phase, I don't know if it's theta 1 and theta 2 or 0 and theta 2 minus theta 1, because it's some general phase. So I can choose theta to be 0, because I can choose one global phase, one and only one in each problem. Questions?
When will it affect?
Hmm?
When will it affect our solution?
When we have more than one. If we have more than one, we need to consider all of them. And then we need to, let's say, have here I theta 1, and at some other place I have E and I theta 2. Then I need to consider like what they, how they interact, what are the relations. But we'll get there.
So the difference would be because of the phase?
And there's going to be a little bit of a phase difference, yes.
But still the probability density would be the same.
Yeah, but the phase could have some time difference. So it might be some phases here now, and then it goes there, and then it gets there.
Dependent on time?
Yeah, but here we don't care because it all depends on time. We don't have any relation. It's very simple. We have one global phase, we set it to 0 and forget about it. Just know it exists. Very, very nice. Very, very nice.
So the second question is, can you just erase now Cn?
No. Because what we did here, we didn't get something which depends on n. Why? How is it possible? Because we had something which depends on n, we had here some an, and we got that an doesn't depend on n. So sometimes it will depend on n, here it doesn't. However, the constant, this general constant is important because this a of n, we need to remember how we got it. We didn't get it from the conditions of the system or the initial conditions or something, which is how we are supposed to get it. We get it from normalization. Because we want phi of x, phi n of x to be normalized. This is how we got it. So we still have some constant which will depend on how much probability weight each mode of phi n of x will get. We'll see it very, very soon.
Which, if we use the probability density as psi or dagger times psi, and not phi.
Here it's phi. You mean the, okay, so.
And then you get Cn squared times An squared. And then it would be equivalent.
If you do it for psi, and we discover it to be 1, we wouldn't be able to find Cn unless you have initial conditions. Do you get some general expression?
No, I know, but An would be dependent on Cn, isn't it?
Like here it's a constant now.
Right, but we just used phi.
But we still have Cn.
But because we used just phi, if we use the entire...
It's not because we used phi, it's because what we did with phi. What we did with phi is we made it be normalized. Okay? We wanted phi of n to be normalized. This is what we wanted to do. What we're gonna have here is still, you see, we have here, so now what we have here something which is called weight. We can call it weight. And here we have some mode, some specific mode. Okay, mode of the wave function. We have many modes, but the initial condition we'll see in a few minutes. And if you have questions, you can ask me again.
Okay. But
what we'll see is that for different initial conditions, you might have only one mode, and if you have only one mode, the weight is going to be 1, and that's it. We're not going to have a full cis. Or let's say we have two modes. The first one is probability of the half, and the second one is also probability half. So we're going to have one mode times half plus the other mode times half. But if you're going to take this and measure this mode, we're going to take the absolute value to measure.
okay.
But what's the probability of this? The probability of this specific mode will be the weight squared. Okay? I'm going to say it one more time because it is important. Wait, let me say it one more time exactly. So, psi of x comma t is going to be equal to weight times mode. This is weight of m, this is mode of m, sum of m. The probability to be at specific mode n is equal to weight n squared. All of these antigen, all the weights are determined by initial conditions. The reason we did this normalizing game is because before, when we didn't have this, the weight and the probability for specific mode was 1. Then the weight was actually a weight for the mode. Now, because we added this constant, the probability for this mode, if we measure this specific mode without any weight, we're going to get coefficient 1. If we're going to take this mode and multiply it by this mode dagger and integrate, or dagger mode, the mode, we're going to get is 1. If it's for the same n, but for this n, of course 0, from orthogonality. This is why it's important physically to understand it, because when we added this constant, the weight became a weight. Cn was a coefficient before, now Cn is a weight. Is the weight, the probability. If you take Cn squared, Cn squared, the weight squared, is going to be the probability that the wave function will be found in a specific moment. Yes, question, ask. We're going to have an example if you want to make this question. It's an example regarding this. Exactly regarding this. This example will be, okay, you have a question right now?
No, ask me.
Yeah, feel free. You have a question? Perfect, okay. So we're gonna do example. Let's say we're gonna solve this problem exactly is psi of x comma t for two different initial conditions. The first one will be psi of x comma 0 equals minus square root of 2 over a sine of 7 pi over a x. The second one will be psi of x comma 0 equals square root of 1 over a sine of 5 pi over a x minus square root of 1 over a sine of 7 pi over a x. Okay. This is a lot of fun. So, for the first initial condition, what is psi of x given t? It's a bit confusing. Let's do it slower. What if psi of x equals 0 in general? It's a sum over n equals 0 to infinity Cn
That's
1 square root of 2 over a sine of n pi over a x. And in this case, for t equals 0, this is the initial conditions. For t equals 0, we know it's also equals to square root of 2 over a sine of 7 pi over a x. What is confusing sometimes is here we have a full series and here we have a single term. So sometimes it takes a little bit of like the coin to fall. Like
orthogonality maybe? And then you
I can use orthogonality, I can have some integration, but I can also write here the full series and use orthogonality. So I can write that what this equation means is that, and let's write this term first. Let's flip the side. We have 2 over a sine of 7 pi over a x equals, and I'm going to write the full series for 1. Equals C1 square root of 2 over a.
Oh, only one mode does some work?
Exactly.
The 7th one?
Exactly. And C2 square root of 2 over a. I'm going to write all the modes until someone is going to yell at me. No, not really. Don't yell at me. I can keep going. But what we see is, because here we have sinus of 7 pi over ax, this one will never coincide because we want those to be equal for any x, the left side and the right side. We're going to have here more terms. One of them is going to be C7 of square root of 2 over a sine of 7 pi x over
Can you
a.
explain again?
Yes.
What you did now?
Okay. This expression we understand, right? Perfect. We have an initial condition where we want the wave function at time 0 to be this expression. So I can write cosine of x at time 0 in two ways. I can write it as the initial condition. That's what I have here. And I can write it as the general series we have right here. And just put t equals 0. And, of course, theta is 0. So I get this full series. So this I understand. Now I can do some fancy tricks, but I want to do it very simple. I can just write the full series here on the left side and write this term. This is the term. And this is the full series. And I can write all the terms, all the coefficients. I open the series, yes, I open the sum, write all the terms explicitly. And then I say, okay, what do I have left? Sometimes it's going to be more complicated than this. It's not going to be the usual method I'm going to solve it. So this is just a first step. So what I'm going to do here, I'm going to say, okay, this is the only term that coincides with this term. If I didn't have sine of 7 pi x over a, I couldn't stand this function with all the other functions. It's similar to the way that sometimes we have some ax cubed, and I'm going to say it's equals to, let's call it b, and then it equals to a0 plus a1x plus a2x squared plus a3x cubed plus dot 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 dot. So you're going to say, okay, the only solution here is if b is equals a3 and ai, which is different than 3, is 0. Meaning all the coefficients here must be 0 except a3, must be equal exactly b. So what we got here? We got that Cn equals 7 is 1, Cn not equal 7 is 0. Hence, the solution is psi of x comma t is 1. This is for C7 times square root of 2 over a times sine of 7 pi over ax times e to the minus I en over h by t, where en is also found using kn. And yes, E7, correct. We got here something very, very interesting. This is a very, very simple example. What we got here is that the mode we started with, which is the 7th mode, is what we're going to have for any time t. Meaning, I'm not going to draw the 7th mode because it's a little bit hard to do it. But if I'm just going to draw, for example, the 2nd mode, which looks like this, let's say this is what I have the solution, this is the only mode that can live. If we start from this mode, this is the only one that can survive, that can be exhibited or measured over time. No other modes live here if this is what we started with. If we start, and we're going to see soon, that if we start with a sum of 2 modes, all we're going to have is 2 modes that live in the system. Questions? Beautiful. No questions. You know everything. You're gonna get the perfect score. What's it? Start with. You can propagate the system exactly. It's weird when it works. And you're gonna get more intuition as we go deeper and deeper. But yes, exactly what we did. We started with some initial conditions in space, and we propagated it in time. We'll later learn about the propagator, which is the shorting equation is like a machine, like a box. When you give it some stuff and you turn it around and it gets out over time. The solution after some kind of time. However, we'll keep it simple for now, before we get too crazy. a. Let's do another example. Woohoo! So much fun. So example 2.
What?
You're smiling too much.
No, what? No, in a good way. In a good
In a good way, in a good
Smile.
way. You're enjoying.
Yeah.
You shouldn't. This is how my supervisor says. You enjoy too much, you shouldn't, you should suffer.
Don't worry, I'll suffer at home.
I hope. I should say to him, yeah. So x, for the second example, x comma z is equals to n equals 0 to infinity. C n square root of 2 over a sine of n pi over a x. Equals to square root of 1 over a sine of 5 pi over a x minus square root of 1 over a sine of 7 pi over a x. I'm sorry at home if you can't see it, probably you can never see it, but this is the term here. Okay, perfect.
Is the 50 going or the 70?
Yes, exactly. So we can say that. Now I'm going to do a leap of faith. I'm going to write that C5 times square root of 2 over a equals square root of 1 over a. C7 times square root of 2 over a equals minus square root of 1 over a. And Ci not equal to 5 and 7 is equal to 0. Does it make sense what I did here? What I did is I expanded the infinite series in my head and I looked only at the terms which live on the right side. C5 is equal to 1 over square root of 0. C7 is equal to 1 over square root of 2. Meaning the probability minus equals to 1 over square root of 2 e to I pi over 2, if I'm not mistaken.
I pi.
I pi.
Yeah, those things pi.
What you see here, okay. So what is the probability to be found at mode 5? What is the probability to be found at mode 7? So what's the difference? We got C5 is not equal, but C5 is not equal to C7. This is we have a phase in C7. What does it mean we have a phase? Why we have a phase on the C7? Because here we have a minus. Because of initial conditions. If I had here plus, we wouldn't have any phase. What does it mean we have a phase?
Interact.
What does it mean? I don't get it.
That's why you say. That's why you say
They're not equal because they're equal up to a phase. So if I'm going to write the wave function for this case, psi of x comma t, I'm going to get let's take square root of 2 over a outside, we don't care about it. Okay? For C5, you're going to get 1 over square root of 2 e to the minus I e5 over h by t sine of 5 pi over x. For the other part, we're going to get, and we can take the 1 over square root of 2 also outside. And we have 1 over a. Plus e to the minus I e 7 over h bar t e to the I pi sine of 7 pi over a e. Questions? What does it mean physically? Okay. Let's assume I had not. Okay, first of all, anyone understood what we did so far? Okay. Let's assume I have this theta of t. Let's say I theta, which is a constant, times t. What I'm gonna get is I'm gonna get here e the minus it e7 over h bar minus t. Meaning, if I have a phasing point, I'm gonna see in the part in the time part. Meaning, when it's not a global phase right now, because when I measure it, I'm gonna still have some. I have like a minus. It's like if this is more 2, what I'm gonna have. This is n equals 2, and if I'm gonna draw n equals 2 in the case we have a phase e to I pi, it's gonna look like this. Okay, if I have two modes like this, so if I propagate over time, so this goes a little bit like this, the other one goes a little bit like that, then we get something which is like this, and something which is in that we get, let's say, like this. So it does have physical meaning, which is one is up, the other one is down. It's still, when you measure it, it doesn't matter in this case. But sometimes when you have something which depends on time, it gets phased over time. Like the phase gets different over time, because it's not going to be here. It's when the phase is constant. If it's not constant, it's going to change over time. The time part is going to behave a little bit different. And we're going to see stuff like this in the future of the things. Question?
Measuring would be different, right?
Yes, because here in this example, if you measure at different points of time, you're going to get different effect of theta. Because if you measure at time equals 0, it doesn't matter what is theta, but let's say time is equal 1. Once in some arbitrary unit, so nothing, you feel this theta, you see.
But now the phase is not
more. No, now it's not. Now it's not the case. Now it's a constant. Now it's a constant, it's a minus, it's almost infinite, it's just opposite to what it's supposed to be.
So that...
Who said I finished?
Finished,
I have another half... No, it was actually great. Let's see if I have something. Okay, so it is important where we start from specific eigenstate, we remain in those eigenstates. And okay, this is the general idea of how we solve time-independent potential Schrödinger equations. Okay. It was a pleasure. Enjoy. Bye-bye.
אז תמיד אנחנו מדביקים את החלק הזמני.
מה זאת אומרת?
אחרי שמצאנו את תנאי ההתחלה וזה, פשוט...
מצאנו תנאי ההתחלה, מדביקים את החלק הזמני. כל הקטע שהתחלנו בלהפריד את החלק הזמני עם החלק המרחבי. לא בכך נוכל לעשות את זה. זאת אומרת, אם הפוטנציאל היה תלוי בזמן, אולי לא היינו יכולים לעשות מההתחלה את ההפרדה הזאת. זה לא יהיה חלק מהקורס, אבל זה כן שאלה מאוד מאוד טובה, כי בסופו של דבר אתה הולך לעבודה, פוטנציאל זה דבר שתלוי בזמן. אתה לא הולך פוטנציאל... I'm gonna switch to English. She asked that the recipe is to always say, okay, we have some partial time, you can just put it in the end, after we figure out what is the special part. And I said, when the potential is independent of time, yes. But when the potential depends on time, which is what actually happens usually, then no. then we might have, we need to solve the Schrödinger equation a little bit differently. What we did here, we started from saying, okay, potential doesn't depend on time, we can solve the Schrödinger anywhere in one dimension, so it's very easy to start solving the Schrödinger equation and just do the separation of variables. However, when the potential does depend on time, for example, when you try to lock a photon, to trap a photon, so you need to do sometimes stuff which is like shooting a laser. When you shoot a laser is the potential. The potential encloses or traps the photon, but it also oscillates in time. It's not going to be part of the course, so if it's very, very hard to understand, it's fine. The focus of the course will be potentials, just for the next few lectures, and it's going to be potentials which are independent of time. יכול להיות שצריך לדחות את התרגול של שבוע הבא. כמו שראשון העביר אותו? כן. אבל...